Do we have the strength to start lecture 9? We think we do? So I have a goal. I have never once made it to the end of lecture 9 in this class. I always run out of time. So this might be the year that I actually get through all the slides live instead of doing a recording after the fact. We'll give it a shot. Those of you who are taking the other class right now will recognize the first set of slides, so it'll be a review. And if you took it last year, then you'll review it then. So I'm not covering path models in this class. I cover them in another class, which is what we're doing right now in the class that meets after this, because path analysis is just about observed variables. But the same principles of path analysis apply when you're fitting a structural model and looking at how your factors relate to each other. So it's at a latent level, in this case, not an observed variable level in most of those. So as a way of trying to review what we've covered this semester then, structural equation modeling is our grand finale. We're finally here. And you will find that it's anticlimactic because all you got to do is put arrows between your factors and it's a structural equation model. And maybe some other stuff in there that you care about. So we have measurement models and structural models, and in terms of the names, I would refer to this measurement model as a CFA if I'm treating the indicators as continuous and I think they're normal enough, in which case there's a linear relationship between the factor and the item response. That means there's nothing that prevents the predicted responses from going out of bounds, which most of you saw when you fit your CFA models to your own data. The logical consequence of the predicted responses going out of bounds is a floor or ceiling effect. Like if you have a 7-point scale and someone's predicted to answer 8, like they can't. So you're going to have a pile of people at the end who said 7 and that's all they could say. To address that limitation, you can fit what is known as an item factor analysis model or an IRT model or a CFA with categorical outcomes. Those are all functionally synonyms to each other. The difference is in what is parameterized. It's IFA or CFA for categorical if you have a model that has factor loadings and thresholds or intercepts. It's IRT if your model is phrased in terms of difficulties or indiscriminations, but they're algebraically rearranged into one another. If the indicators are binary or ordinal. If you have a nominal indicator, I spent about 10 seconds talking about that because that one's hard. But there is a really good article on your reading list, it's a tutorial about those models. That's where I would direct you to. It's called IRT, and there is no limited information version of nominal models. There's no way to hack a bivariate normal distribution to create some kind of like polychoric or tetrachoric correlation if your indicators are nominal. So there's no way to do that. So if you have nominal indicators, then you are stuck with full information and all of the estimation difficulty that brings. I don't know what it's called if the indicators have some other kind of link function, but I know that it's possible. So if you have counts of behaviors, or like the kids deciding to break or not break and then how long it took them to break thing, anything like that you can have as indicators as a latent factor, it just doesn't have a special name. You might call that generalized structural equation modeling. That sounds pretty fancy, right? Like if you're in a job talk and you're like, hey, I got quant cred, I'm going to do a generalized latent variable model. Like that sounds pretty cool, right? I think so. You could actually use that phrase for any of these because generalized is like an umbrella term that encompasses everything, but that would be what I would call it as opposed to which is maybe not the best name when you're giving a job talk. Like theoretically, you could have binomial outcomes, but I don't know of any software that would let you. Maybe Stata GSIM, but I'm not 100 on that. In every case, though, the latent variable itself, so I've got 3 synonyms here, factors, thetas, traits. Give me some more. We got a whole list. Other synonyms for the idea of a latent variable.
True score. True score?
True score. Dimensions, I'll take that. Latent as a prefix has a bunch of words after it. Variable, factor, construct. Theta and true score from the classical test theory and item response theory worlds. Ability is what it's called if you're in an educational context. Random intercepts, random slopes. Those are some synonyms too. Whatever you call it, in every case though, they're assumed to be multivariate normal. Like that's not something that you'll find in standard software to have something else. The only other thing that would be standard is to consider them to be categorical variables. And that is the world of latent class, latent profile, latent trajectory, and mixture models broadly construed. That's when you say your trait is actually a category. Like you have this problem or you don't. Or you're proficient in this skill or you're not. If you want those kinds of models, then that is the world of diagnostic classification models. If it's confirmatory, if it's exploratory, then it's all the other words I said. Mixture models broadly construed. Structural model then is nothing but path analysis using these multivariate normal latent variables. So at this step, it's like the CFA, like there's no link functions or anything unless you're predicting something that is not normal. But the factors themselves are considered normally distributed. So you can put into a structural equation model any other observed variable that you want. It can be its own thing. It does not have to be an indicator of a latent variable. It can just be standalone. So for instance, in the last slide on the previous thing here, this is considered a structural equation model, slide 28. The one outcome that they wanted to predict was this binary box right here, and that was the whole point. But in order to adequately measure all of the traits they wanted to predict it with, this part was built on measurement models. Timing and pubertal timing in girl versus boy were other predictors in their observed boxes as well. So you can have any combination of latent or observed. You can have things that are covariate with the two-headed arrows. You can have things that are directed. So the same idea in terms of what we called loadings as slopes also operate here. So a directed arrow is a slope predicting the outcome from the predictor. Any combination of those that you want. One catch though, if you have a binary predictor, you do not have to put it on the categorical statement. So that is only for binary outcomes, things that are going to be predicted. So if you just have a dummy code for, some covariate, just put it in the model as is. You don't have to tell it that it's binary. If you have a categorical predictor, though, what I would call a factor variable, you are out of luck in an M+. M+ has no class statement, no I dot, no factor variable, no nothing. You got to make a million dummy codes if you're stuck with that. That is especially painful if you're trying to fit like a fixed effect model to address cluster dependency, which I found this week. I tried to do one to control for the differences across 12 schools, and M+ was just like, no, I'm not doing it. And I don't know why. So that part gets a little bit tricky. Model identification in SEM is a big deal if you read about it in the textbooks, and I'm telling you, don't bother. Like, don't worry about this, okay? You need to make sure that your factors are identified, that each factor has a mean and a variance, and that it has enough degrees of freedom to be locally identified. There's all kinds of rules about how to figure out if your model is identified overall as a structural equation model. If you don't do things that are stupid, you're good. And by stupid, I mean redundant. Like, don't put a directed arrow to something and then a covariance with the same thing, right? You can't have two relationships out of one relationship. Like, don't do stuff like that and you're fine. It's usually the measurement model that's the problem if something is under-identified. And you'll know that because you would have fit that separately to check on it first. I also would not recommend having negative and positive factor loadings because then the model doesn't know which way is up. If you need to do it that way for some reason, I would probably fix the factor loading in the direction that you want it to go to 1. That way the rest of them fall align relative to that as an anchor point. So like with the optimism and pessimism example, if you want the scale to be optimism, then the positive loadings fix one of those to 1, and that will anchor the factor in the direction that you want it to go as to what more means. All right. Nah, I don't want to do this yet. I think that's enough for today. Because it's 1:37. Yeah, and the next set of things is like a longer thing than 7 minutes. So no, we'll just be done early. How's that sound? Would you like 7 minutes of your life back? Zoomers are like, yes, bye. All right, any questions in the 7 minutes that we have left? All right, well, if you think of questions, let me or the TAs know. Thank you for being here. Have good weekends. Do your formative assessment. Try homework 6, and I'll see you next week. How's that? All right. Bye for now.